Today is December 14th, 2025. Have you observed 3i Atlas flipped his anti-tail pointing toward Earth? And you guys already know that we are no longer looking at a standard celestial event. We are looking at a mystery that is deepening by the hour. Over the last 24 hours, a flood of new data has come in from independent observatories and major astronomical networks alike. And what we are seeing is frankly baffling. Before we unravel this spiderweb of data, if you want to stay ahead of these rapid developments, because this story is changing literally overnight, hit that subscribe button right now and turn on notifications. We are tracking this in real time, and you do not want to miss the analysis of the Hubble data coming in the next few days. The images we're about to show you will change how you think about what's possible in our solar system. We are not just talking about a comet getting brighter or dimming as it moves away from the sun. We are talking about a fundamental shift in morphology that defies our standard models of cometary evaporation. The object is changing shape. It is pulsing with activity, and the latest images from December 13th and 14th reveal a structure that looks less like a dirty snowball and more like something alive with energy. Something that seems to be responding to forces we don't yet understand. Forces that might be internal rather than external. Forces that challenge every assumption we've made about how interstellar visitors should behave when they pass through our cosmic neighbourhood. Let's look at the data, the raw observational facts that are forcing astronomers to reconsider everything they thought they knew about comets. The headline today is the spider anomaly. When we look at comets, we typically expect a coma, that fuzzy envelope of gas and dust surrounding the nucleus, and a tail usually streaming away from the sun driven by solar wind and radiation pressure. It is a passive process, governed by simple physics that we've understood for centuries. The sun heats the ice on the comet's surface. The ice sublimates, turning directly from solid to gas without passing through liquid phase, and the resulting gas and entrained dust particles get pushed back by solar radiation pressure and the charged particles of the solar wind. Simple, predictable, something we can model with high accuracy using standard equations of heat transfer and particle dynamics. But 3i Atlas is refusing to play by these rules. It's not following the script that every comet we've studied for the past 100 years has followed. The freshest images processed late last night by teams at multiple observatories show a tail structure that is fragmented into what astronomers are calling a spider-like morphology. Instead of a single sweeping fan of dust extending millions of kilometers behind the nucleus in a graceful curve, instead of the beautiful streamers we associate with spectacular comets like Hale-Bopp or McNaught, we are seeing something that looks fundamentally different. We're seeing short, narrow jets diverging in multiple directions from the central nucleus, each one discrete and well-defined rather than blending into a diffuse tail. It looks like the legs of a spider extending from a central body, radiating outward in patterns that suggest organization rather than chaos, structure rather than random ejection. This contradicts what we previously thought about the stability of this object. Just days ago, as 3i Atlas passed through perihelion, its closest approach to the Sun on late October 2024, we assumed that the intense solar heating would trigger massive outgassing that would then stabilize as the comet moved away and cooled down. We expected the outgassing to follow a predictable curve, peaking at perihelion and then declining smoothly as the object receded and surface temperatures dropped. That's what every comet we've studied does. That's what the physics demands should happen. Heat input decreases with the square of distance from the sun, sublimation rates drop exponentially with temperature, and activity fades in ways we can calculate precisely. Instead, we are seeing chaotic episodic outbursts that don't correlate with solar distance in the expected ways. These jets are not static, not like a faucet that has been left running with steady flow. They are flashing, appearing suddenly without warning, shooting out material with immense velocity measured in hundreds of meters per second, changing direction as if responding to internal pressure changes, weakening and fading, and then disappearing completely only to reappear hours later in a different sector of the coma, from a different location on the nucleus, with different intensity and different composition. This is high-frequency temporal variability on timescales of hours rather than days or weeks. Variability that suggests the surface of the nucleus is not sublimating evenly in response to solar heating, but is instead experiencing discrete explosive events. It implies that there are specific active regions on the surface, vents if you will, localized sources where subsurface pressure has built up until it exceeds the strength of the overlying material, triggering explosively as that material fractures and allows sudden release of gas and dust, and then shutting down when pressure equalizes, only to build up again in a different location as heat continues penetrating into the interior through different pathways. Imagine a pressure cooker where the valve doesn't just hiss steadily, releasing steam at a controlled rate, but instead pops open violently at random intervals with explosive force, spinning the pot as it does so, creating thrust vectors that push the pot around the stove. That is the kind of dynamic instability we are witnessing in 3I Atlas right now. The nucleus is not passively responding to external heating. It's actively erupting in ways that look almost like controlled releases, though we're not prepared to use that word officially yet. The jets are even being observed directed toward the sun, which is highly atypical for standard dust or ion tail structures. Let me explain why this is so strange. Solar radiation pressure, the physical push exerted by photons streaming from the sun, should be overwhelming these emissions, pushing them back away from the sun regardless of the initial ejection direction. The force from radiation pressure on small particles, dust grains measured in micrometers diameter, is immense at this distance from the sun. Those particles should be swept backward into the anti-solar direction within minutes of ejection, creating the characteristic tail that always points away from the sun even when the comet is receding and moving in the opposite direction from the tail. The fact that these jets can punch upstream against the solar wind, that they can maintain sunward pointing trajectories, suggests they are being ejected with significant force, with velocities high enough that momentum carries the particles on ballistic trajectories before radiation pressure can turn them around. This isn't just evaporation, gentle sublimation driven by passive solar heating. This is propulsion, explosive ejection driven by pressure release that imparts high velocity to material being expelled. The implications are profound because the energy required to produce such ejection velocities is enormous, far exceeding what simple solar heating of surface ices can provide, unless there are focusing mechanisms, subsurface cavities where pressure builds, or volatile ices with much higher vapor pressure than water ice. The coma itself, the diffuse envelope of gas and dust surrounding the nucleus, is demonstrating behavior that is equally puzzling and equally difficult to reconcile with standard cometary models. We are seeing what looks like cyclone-like turbulent motion in the coma, swirling patterns visible in images taken with different filters that isolate specific emission lines from different molecules. The gas and dust envelope isn't just expanding outward in a smooth sphere, a sublimated material escapes from the surface and diffuses into space. It is swirling, showing rotation, displaying vortex structures that suggest organized motion rather than random thermal expansion. This could be caused by the rapid rotation of the nucleus itself, the solid body spinning and dragging the inner coma along with it through viscous coupling, which we will discuss in much more detail later when we examine the rotation state. Or it could be evidence of uneven heating creating massive thermal differentials on the surface, where the hot day side is releasing gas at high rates while the cold night side is inactive, and the transition region between day and night produces strong lateral flows as pressure gradients drive gas from high pressure regions to low pressure regions. But there is another possibility that we must consider, one that's more disturbing and more difficult to explain through natural processes alone: structural stresses within the nucleus causing the surface to fracture asymmetrically. If the nucleus is not a solid monolithic block of ice, which we strongly suspect it isn't because most comets appear to be loosely consolidated rubble piles, but rather a loose agglomeration of rock fragments, ice chunks, and exotic ices containing molecules more volatile than water, or perhaps something with a rigid crust overlying a volatile-rich interior where pressure is building as subsurface ices warm and sublimate, without escape routes to the surface, then these internal stresses could be causing the surface to fracture catastrophically. The fractures would release these spider legs of gas in violent bursts as previously sealed reservoirs suddenly open to space, venting their contents explosively in directions determined by the geometry of the fracture network rather than by where the sun is located. The activity assessment as of December 14th, based on spectroscopic measurements from multiple observatories monitoring the coma composition, is off the charts in terms of gas production rates. We are seeing a gas component that is incredibly high relative to the dust, a dust-to-gas ratio that's much lower than typical comets show. Most comets have dust-to-gas ratios around 0.3 to 1.0, meaning they release comparable amounts of dust and gas by mass. 3i Atlas is currently showing ratios around 0.1 or even lower in some measurements, meaning gas dominates the emission by an order of magnitude. This is characteristic of very fresh unweathered cometary surfaces, or of compositions dominated by super volatile ices like carbon monoxide or carbon dioxide that sublimate more readily than water ice and don't carry as much dust with them. But the composition is where it gets really strange, where we start seeing chemical signatures that don't match what we expect from solar system comets. We are detecting elevated nickel content compared to iron in the spectral lines from metallic atoms in the coma. Comets usually have a specific ratio of these metals, a nickel to iron ratio around 0.06, meaning iron is about 17 times more abundant than nickel, reflecting the cosmic abundances of these elements in the primordial solar nebula from which our solar system formed 4.6 billion years ago. But 3i Atlas is breaking that ratio, showing nickel abundance much higher relative to iron than solar system materials display. Why is there so much nickel? This is not a trivial question. It has profound implications for where this object formed. Is the nickel exposed on the surface in metallic form, perhaps as part of a differentiated core that got exposed when an outer mantle was stripped away by some ancient collision? Is it being dredged up from a deep metallic core as the surface erodes and internal structure becomes exposed? Or is the entire object made of something different than the primordial soup of our own solar system, material that condensed in a protoplanetary disk around a different star with different metallicity, different elemental abundances, different chemical conditions that favoured nickel incorporation over iron? The morphological stability of 3i Atlas is currently rated as low by teams trying to track and characterise the object. That is scientific politeness, the understated language astronomers use for this thing is falling apart or transforming right in front of us in ways we can't predict. The shape you see in an image taken at 2 a.m. UTC might be completely different from the shape visible in an image taken at 4 a.m. just 2 hours later. Features appear and disappear on timescales of hours, the boundaries of the coma shift, the jet structures reconfigure. This high temporal variability is the smoking gun that tells us unambiguously that this is not a passive rock responding slowly to changing solar illumination. It is an active, dynamic system, an engine of some kind, whether natural or otherwise, operating on internal timescales much faster than external forcing. The spider shape we're seeing right now is likely a transient phase, a snapshot of a chaotic process where the object is shedding mass in a highly non-uniform way, perhaps because it's fragmenting, perhaps because it's adjusting to internal pressure changes, perhaps because whatever is driving the jets is cycling through different states. This is not a stable configuration that will persist. It's a moment in an evolution we're witnessing in real time. So what does this actually mean for our understanding of what 3i Atlas is? It means fundamentally that we cannot predict what it will look like tomorrow with any confidence. Standard cometary models, the sophisticated codes that integrate heat transfer and gas dynamics and have been validated against hundreds of comet observations, those models are failing to predict even the basic morphology. If these outbursts continue at the current rate, if the jets keep firing and reconfiguring, the spider could evolve into completely different structures. It might expand into a ring as material gets ejected in all directions, creating a toroidal distribution. It might spiral as rotation couples with asymmetric jetting to create angular momentum transport. Or it might fragment completely as internal stresses exceed the structural strength of whatever is holding the nucleus together, breaking into multiple pieces that would then follow slightly different trajectories and could be tracked separately. But there is one feature that has persisted through all of these changes, one structure that has remained visible and identifiable even as everything else shifted and reconfigured, one feature that is even stranger than the flashing jets and the turbulent coma, one feature that should not exist according to our understanding of how cometary tails form and evolve. As we move our attention from the chaotic coma, from that explosive spider-like structure immediately surrounding the nucleus, to the tail structure extending behind the comet, we find something that shouldn't be there at all according to standard physics. We find a structure that seems to defy the geometry of solar radiation pressure and solar wind momentum transfer. As we established, the jets are firing in all directions, creating this spider effect, creating a roughly spherical or at least multi-directional emission pattern. But amidst this chaos, amidst this seemingly random explosive activity, a distinct organized structure has emerged that is drawing intense attention from observers, including heavyweights like Avi Loeb, who has been documenting this feature extensively. It is called the anti-tail, though that name doesn't really do justice to how strange this feature actually is. And unlike the flickering jets, unlike the transient spider legs that appear and disappear, this feature is behaving with what observers are calling a disturbing kind of persistence. It's maintaining its integrity over days. It's not just a trick of perspective, not just a projection effect where we happen to be looking at normal tail material from an edge-on angle that makes it appear to point in strange directions. It is a physical structure, a genuine condensation of material, a swarm of particles or objects that is pointing in a direction that makes astronomers very uncomfortable because that direction doesn't align with where solar radiation pressure should push material. Building on this observation, we have to ask a fundamental question. If the jets are the engine, if they're the source of the explosive activity we're seeing in the coma, then what is the anti-tail? Is it the exhaust from those jets, the material that's been ejected and is now following ballistic trajectories? Or is it something else entirely, something with different origin, different dynamics? The data from December 14th, the latest measurements, give us a clue about what's happening, and that clue involves a flip that has just occurred, a sudden change in the configuration of this structure that has profound implications for understanding what it's made of. The object has passed perihelion, has swung around the sun, and is now receding on the outbound leg of its hyperbolic trajectory. Usually for comets making this transition, the geometry of the tail changes in a predictable way. Material that was being pushed behind the comet when it was approaching the sun gets swept into different configurations as the comet moves past perihelion and starts receding. The tail pivots, maintaining its anti-solar orientation, always pointing away from the sun even as the comet's motion direction reverses. But the anti-tail of 3I Atlas has done something different. It has rotated, but not in the way a normal dust tail would rotate. It has flipped its orientation relative to the sun while maintaining a coherence, a structural integrity that suggests it is made of heavy, massive particles that are not easily pushed around by sunlight. These particles have so much momentum, so much inertia, that radiation pressure cannot redirect them quickly. They're following trajectories determined by their initial ejection velocity and by gravity, not by radiation pressure. This connects directly to the next phase of our investigation into what this object truly represents. We have the spider jets indicating a volatile explosive surface, activity that's generating enormous amounts of gas and some dust, but with unusual composition and unusual dynamics. But trailing behind this explosive nucleus, or perhaps leading ahead of it depending on viewing geometry and orbital position, is this dense, mysterious swarm of material that the anti-tail represents. It is a duality that fundamentally defines 3I Atlas, two completely different regimes of behavior coexisting in the same object. The chaotic gaseous explosion of the coma with its flashing jets and turbulent motions, and the heavy silent persistence of the anti-tail, maintaining its structure over days and weeks despite forces that should disperse it. To understand what this object truly is, we have to understand what it is leaving behind. And the latest reports, the December 14th assessments, from teams analysing the highest resolution images, describe this anti-tail not as a simple stream of dust particles, like what you'd see from a normal comet, but as what they're calling a swarm of unknown objects. Let that sink in for a moment. Not dust, not gas. Unknown objects in a swarm configuration. We are going to dissect exactly what that means, what the observational evidence is for this interpretation, and why this swarm configuration might be significant in ways that go far beyond just unusual dust dynamics in the next part of our deep dive. The spider is just the beginning, the visible manifestation of whatever is happening on and in the nucleus. The web it is weaving through space, the structures it's creating, these are far more complex than anything we've seen from interstellar visitors before. This is not Oumuamua with its simple, elongated shape and smooth trajectory. This is not 2I Borisov that looked and behaved like a normal comet despite coming from another star. This is something that's challenging our categories, forcing us to question whether our frameworks for understanding cosmic visitors are adequate, whether the distinction between comet and asteroid and probe is as clear as we thought it was, whether nature has surprises for us that we haven't anticipated because our experience has been limited to objects born in our own solar system, following familiar patterns established over billions of years of observation. and as December marches toward the critical observation window, on December 19th, when Earth's viewing geometry will be optimal, when we'll be looking directly down the axis of that mysterious anti-tail, as Hubble prepares to turn its acute vision toward this enigmatic visitor, and as GSM readies its X-ray detectors to probe the energetics of the coma, we stand on the verge of answers that might confirm our hopes for understanding, or might instead raise more questions than they answer, might force us to accept that the universe is stranger than our theories accommodate, that interstellar space harbours phenomena we've never imagined, because we've never had the capability to detect them until now, when surveys like Atlas and Pan-STARRS scan the entire sky every night, looking for anything that moves against the background stars, and we're finally beginning to inventory what's actually out there passing through our cosmic neighbourhood at any given moment. The story of 3i Atlas is unfolding in real time, developing faster than we can write papers to describe it, changing more rapidly than peer review can keep pace with, demanding that we share raw observations and preliminary interpretations through rapid communication channels like the astronomer's telegram and conference presentations, rather than waiting months for formal publication. This is science at its most exciting and most frustrating, where every new dataset potentially overturns yesterday's conclusions, where certainty evaporates in the face of new evidence, where researchers are forced to acknowledge that they don't know what they're looking at even as they scramble to collect more data to constrain possibilities. So buckle in, because what we're about to explore in the subsequent parts of this analysis will take us from the chaotic spider jets through the mysterious swarm anti-tail into the chemical composition revealing exotic elements, through the energetics showing X-ray emission that shouldn't exist, into the orbital dynamics demonstrating non-gravitational forces that seem organized rather than random, and finally to the question that nobody wants to ask out loud, but that lurks beneath every conversation about this object. What if we're not looking at a comet at all? What if the categories we've created, natural versus artificial, icy versus rocky, active versus inert, what if these categories are inadequate for classifying something that formed under completely different conditions billions of years ago in a stellar system, nothing like our own, and has been wandering through interstellar space for millions or billions of years, experiencing environments and processes we can barely imagine? Part 2 awaits, where we will examine the anti-tail in excruciating detail, where we will look at why Avi Loeb and other serious researchers are using words like swarm and unknown objects, rather than comfortable familiar terms like dust trail, where we will confront the observational evidence that this structure has mass and coherence and behaviour that don't fit simple models, where we will calculate what it would take for material to maintain the configurations we're observing, and where we will begin to seriously consider whether the distinction between natural and artificial might be less clear than we've assumed when we're dealing with phenomena at scales and in environments so far removed from human experience that our intuitions about what's possible and what's not become unreliable guides to reality, where the only arbiter of truth is the data itself, raw photons collected by telescopes and analysed with mathematical rigour, telling us what is rather than what we wish or expect, forcing us to follow evidence even when it leads to conclusions that make us uncomfortable or uncertain about frameworks we thought were solid. We establish that this is not normal cometary behaviour, not the passive response to solar heating that we see in every other comet we've studied. But as dramatic as those spider jets are, as visually striking as the turbulent coma appears in fresh images, they pale in significance compared to what we're about to examine. Because as we shift our focus from the immediate vicinity of the nucleus to the broader structure extending behind or around the comet, we encounter a phenomenon that is perhaps even more unsettling to researchers who have dedicated their careers to understanding how comets work. It is the feature that has kept Avi Loeb and independent astronomers awake for the last few nights. The structure that is generating intense debate in professional circles, the observation that some are calling the most anomalous aspect of an already deeply anomalous object, the anti-tail. Now, here is the crucial detail that you need to understand before we can properly analyse what we're seeing. Usually an anti-tail, when astronomers use that term, is referring to an optical illusion, a projection effect that has a perfectly mundane explanation. It happens when Earth crosses the orbital plane of a comet, when our viewing geometry changes such that we see the comet's dust trail edge on, rather than from above or below. When you look at a sheet of material edge on, when you're looking along its plane rather than perpendicular to it, you see all the particles along that line of sight superimposed, creating a concentrated bright feature. This edge-on view of the dust trail can create what looks like a spike pointing toward the sun, appearing to violate the normal rule that comet tails always point away from the sun. But it's just geometry, just perspective, like how a long straight road can appear to come to a point when you look down its length, even though the road itself isn't converging. The particles are still being pushed away from the sun by radiation pressure, still following the normal physics, but our viewing angle makes them appear to point sunward. Astronomers understand this effect thoroughly. We can predict exactly when anti-tails should appear based on orbital geometry, and observations always match predictions. It is a solved problem, a sostopa, well-characterized phenomenon that doesn't generate any controversy or mystery when we see it. But for 3i Atlas, the geometry doesn't quite add up to a simple illusion anymore. The timing is wrong, the persistence is wrong, the behavior is wrong. The latest data from December 14th describes this feature not as a passive projection effect, not as an artifact of viewing geometry, but as something physical and dynamic. It describes this anti-tail not as a dust trail we're seeing edge on, but as what multiple independent observers are now calling a swarm of unknown objects arranged in a droplet shape. Those words carry enormous weight. Unknown objects. Swarm. These are not terms astronomers use casually, not descriptions they apply to normal cometary dust. And most critically, most problematically for conventional explanations, this structure has flipped. Avi Loeb has emphasized this point repeatedly in his recent reports, has highlighted it as one of the key observations that demands explanation beyond standard cometary physics. After perihelion, after the point of closest approach to the Sun when 3i Atlas swung around at minimum distance experiencing maximum solar heating and maximum gravitational acceleration, the anti-tail didn't behave like a standard dust trail should behave. It didn't disperse, it didn't fade, it didn't gradually thin out as particles spread along their individual orbits. Instead, it rotated. It maintained its integrity as a coherent structure. It flipped its orientation in a way that suggests it is not reacting to solar radiation pressure the way typical cometary dust does, not responding to the dominant force that should be controlling its motion. If this were fine dust, the kind of micron-sized grains that normally comprise cometary tails, those particles form through sublimation, breaking down surface material and releasing tiny fragments. The solar wind would have blown it back, dispersed it into a diffuse fan expanding outward from the nucleus. Solar radiation pressure on small particles is immense. The acceleration is inversely proportional to particle size, so smaller particles experience stronger relative force. For micron-sized dust at 1 AU from the Sun, radiation pressure acceleration can exceed solar gravity by factors of 10 or more, meaning these particles are flung outward at tremendous speeds, creating the long, graceful tails that extend millions of kilometers from bright comets. But the anti-tail of 3i Atlas hasn't dispersed despite being subjected to these forces for weeks. It has remained tight, compact, maintaining a high surface brightness that indicates concentrated material rather than diffuse spread. It has remained coherent, with sharp boundaries visible in high-resolution images rather than the fuzzy edges you'd expect from a dispersing dust cloud. And it has remained highly reflective, catching sunlight efficiently, showing up prominently in images despite the relatively small amount of material it must contain compared to the much larger diffuse coma. This insensitivity to solar radiation pressure is a massive red flag, an observation that immediately tells experienced researchers that whatever comprises this structure is not behaving like normal dust. It implies that the particles making up this anti-tail are large relative to typical cometary dust. They are heavy, with high mass-to-cross-section ratios. They are too massive for the pressure of sunlight to push them around effectively, too inertial to respond quickly to radiation pressure forces. We are not talking about micron-sized grains of soot here, not the fluffy aggregates of sub-micron particles that sublimation typically releases. We are potentially talking about pebbles, about centimetre or larger fragments. We are talking about boulders, metre-scale rocks. We are talking about chunks of refractory material, high-temperature minerals and metals that can withstand intense solar heating, without vaporizing, without sublimating away into gas. The description of a swarm is deliberate and significant. Loeb and others aren't using this word accidentally or for dramatic effect. It is a carefully chosen technical term that suggests a collection of discrete bodies, individual objects moving in formation, rather than a continuous fluid of gas and dust. It suggests particles or fragments that maintain their identity, that don't coalesce into larger bodies or fragment into smaller ones, that follow individual trajectories while remaining gravitationally or dynamically associated with each other and with the main nucleus. A swarm has structure, it has organization, it implies collective behavior emerging from the motions of many individual components. Let's look at the specific positional and velocity data we have as of December 14th, because these numbers are crucial for understanding what we're dealing with. The comet nucleus, the central body from which everything else originates, is approximately 270 million kilometers from Earth right now. That's about 1.8 AU, 1.8 times the Earth-Sun distance. It's not particularly close in cosmic terms, but it's close enough for good observations with professional telescopes and even with high-end amateur equipment. The object is moving at a blistering speed relative to the Sun of 63.7 kilometers per second, roughly 230,000 kilometers per hour, which is typical for hyperbolic interstellar trajectories, but still impressive when you think about the kinetic energy involved. And crucially, it is accelerating, not just moving at constant velocity as a purely ballistic object following a gravitational trajectory would, but actually increasing its speed, gaining velocity beyond what solar gravity alone predicts. This acceleration will be central to our discussion later when we examine the non-gravitational forces, the deviations from pure Keplerian orbital motion that indicate the object is experiencing thrust from somewhere, either from natural outgassing or from something else. The anti-tail, this mysterious swarm structure, persists in observations taken after perihelion. It didn't disappear or fade away as the comet moved past closest approach and began receding. It is still there, still visible, still maintaining coherence weeks after it should have dispersed if it were normal dust. And due to the orbital geometry, due to the relative positions of the comet, Earth, and the Sun changing as everything moves through space following their respective orbits, this swarm may be directed toward Earth by December 19th. That's 5 days from now. 5 days until our viewing angle will place us looking directly down the axis of this structure, seeing it head-on rather than from the side, optimal geometry for determining what it actually is. Now let me be very clear about what this does and doesn't mean, because I don't want to create unnecessary alarm. This alignment does not mean a collision is imminent. The distances involved are still enormous. The swarm material is distributed over a volume millions of kilometers in extent, and even if some of it is on trajectories that will eventually cross Earth's orbital path, the probability of any significant particle actually hitting Earth is vanishingly small. We're not looking at an impact scenario. Space is big, really big, and even dense swarms by astronomical standards are mostly empty space at human scales. What this alignment does mean, what makes December 19th so significant, is that we're going to get a front row view of this structure. We're going to be looking right down the barrel of this swarm, seeing it from a perspective that reveals its three-dimensional structure, rather than just a two-dimensional projection. We'll be able to measure the radial velocities of components, the speeds at which particles are moving toward or away from us. We'll be able to assess the density distribution, how concentrated the material is. We'll be able to determine whether it's a single coherent cloud or multiple distinct clumps. This alignment provides a unique scientific opportunity to characterize what is perhaps the strangest aspect of an already strange object. This geometry is optimal for what astronomers call scattering phase angle analysis, for understanding how the material reflects sunlight from different angles, which tells you about particle size and composition. It's perfect for spectroscopy because you're looking through the maximum column density of material, getting the strongest possible signal from molecules and atoms in the swarm. And it's ideal for detecting any temporal variations, any changes in brightness or structure that might indicate dynamic processes still occurring within the swarm. But beyond the scientific value, this alignment raises questions that make researchers uncomfortable. If the anti-tail is made of heavy rocky fragments, large particles that can survive solar heating and resist radiation pressure, where did they come from? How did they get into this configuration? What ejection mechanism can produce a swarm of large debris moving in formation? A typical comet is mostly ice, water ice mixed with various other frozen volatiles, all laced with dust grains and small rock fragments. The ice is the dominant component by mass. When a comet approaches the Sun, the ice sublimates, turning directly from solid to gas, and as it does so, it releases the embedded dust particles which get carried along with the expanding gas. But this process produces small particles, micron to millimetre scale, occasionally larger but rarely exceeding centimetres. You don't get metre-scale boulders from sublimation of ice unless something more violent is happening, unless the nucleus is fracturing, unless large pieces of crust are being shed as underlying ice sublimate undermines structural support. The high reflectivity of the swarm is also puzzling and creates another layer of mystery. Dark carbon-rich asteroids, the kind of primitive objects that formed in the outer solar system and should be compositionally similar to comets, are not very reflective. They have low albedos, meaning they absorb most incident sunlight rather than reflecting it. These dark surfaces make sense for objects that have been exposed to cosmic radiation and solar heating for billions of years, gradually converting surface organics into complex carbon compounds that darken with time. Ice, by contrast, is highly reflective. Fresh clean ice has an albedo approaching 1.0, reflecting nearly all incident light, which is why glaciers and snow-covered landscapes are so bright. But ice should have sublimated completely at the distance from the Sun where 3I Atlas passed perihelion, or at minimum should have been blown away by solar wind dispersed into the diffuse coma. So we have this paradox, a swarm of heavy objects that are also shiny. What material fits that profile? What composition can be both massive enough to resist radiation pressure and reflective enough to show up prominently in images? One possibility is refractory dust, silicate particles that have been processed by high temperatures, perhaps in the protostellar nebula where 3I Atlas formed, creating crystalline structures with relatively high reflectivity. Silicates can have albedos around 0.3 to 0.6 depending on composition and crystallinity, bright enough to be visible, but not as bright as ice. Another possibility is metallic fragments, perhaps nickel-iron particles given the elevated nickel abundances we're seeing in spectroscopic measurements of the coma. Metals can be highly reflective when fresh, though they tarnish and darken with time when exposed to space weathering. A third possibility, more exotic but consistent with some of the other anomalies we've documented, is that the swarm contains ices more refractory than water ice, compounds that remain solid at temperatures where water would sublimate. Nitrogen ice, carbon monoxide ice. These can exist at higher temperatures than water ice under certain pressure conditions. Or perhaps we're seeing clathrate structures, cage-like molecular frameworks where volatile molecules are trapped in ice lattices in ways that stabilize them against sublimation. This brings us to the droplet shape that observers are reporting, a configuration that adds yet another puzzle to an already confusing picture. A droplet implies a specific geometry, a rounded teardrop-like distribution of material that's wider at one end and tapers to a point at the other. In fluid dynamics on Earth, droplets form because of surface tension, the cohesive forces between molecules that minimize surface area and create stable rounded shapes. But surface tension doesn't exist in the vacuum of space. There's no fluid interface, no surface separating inside from outside the way there is with a water droplet in air. So why would a swarm of discrete particles in space adopt a droplet shape? One possibility is that it's an aerodynamic or hydrodynamic shaping by solar wind, the charged particles streaming from the sun interacting with the swarm and sculpting its outer boundary. If the swarm is dense enough that particles collide frequently, if there's enough material that collective behavior emerges, then solar wind pressure could compress the upstream side facing the sun while allowing expansion on the downstream side, creating an asymmetric teardrop profile. But if the material is insensitive to solar wind, as we've argued, based on the lack of dispersion and the resistance to radiation pressure, why would the droplet shape form? It suggests that something else is controlling the distribution, that the ejection mechanism that created this swarm was directional rather than spherical. It wasn't an explosion that threw material out in all directions equally. It was a directed release, a jet, or a plume, or a focused expulsion that concentrated material along a preferred axis. I want to pause here and ask you a question directly. Engage with you as fellow observers of this mystery. If you were looking at an object that had, on one hand, a chaotic explosive engine at the front generating those spider jets we discussed, episodic violent outbursts of gas creating turbulent swirling motions in the coma, and on the other hand, a heavy coherent non-reactive structure trailing behind it, maintaining stable configuration over weeks, would you still comfortably call it a comet? Or would you start looking for other definitions, other categories that might fit better? Let me know in the comments what you think this swarm actually is. Give me your hypothesis. Is it debris from natural fragmentation, chunks of nucleus material that broke off during violent outgassing? Is it something that was released intentionally, material ejected for some purpose we can't determine? Or is it something we don't have a name for yet, something that doesn't fit neatly into our existing taxonomies of solar system objects, because it formed under conditions we don't encounter in our own system? So what does the flip of this antitail structure actually tell us? Why is Avi Loeb emphasizing this observation so strongly in his recent analyses? The flip indicates that the orientation of this swarm is tied to the orbital dynamics of the main body in what appears to be a rigid way. The swarm isn't floating freely, dispersing and diffusing as individual particles follow their own independent trajectories, determined by their ejection velocities and solar radiation pressure. Instead, it's moving like a rigid extension of the nucleus, like a solid rod attached to the main body, maintaining its structural integrity and rotating as a unit when the nucleus's motion changes direction. This is profoundly weird if you understand how cometary tails normally behave. Normal tails are fluid, dynamic, constantly reforming as new material gets released from the nucleus, and old material disperses or gets left behind along the orbit. The tail you see today contains different particles than the tail you saw yesterday. It's not a fixed structure, but a continuously renewed feature. Like the wake behind a boat where the water forming the wake is constantly being replaced, but the pattern persists because of the continuing motion of the boat. But this swarm is behaving more like a solid object, maintaining its identity over time, rotating when the nucleus rotates, following the nucleus's trajectory changes rather than continuing on independent paths. This rigid coupling is exactly the opposite of what you'd expect from material that's been ejected and is now subject to solar forces. Once particles leave the nucleus, once they're no longer in physical contact with the main body, they should follow their own independent ballistic trajectories. They shouldn't remain coupled to the nucleus's motion. This adds to the multitude of anomalies that Loeb has been documenting systematically in his reports and presentations. He points out that if this were a natural fragmentation process, if the swarm formed from the nucleus breaking apart or shedding large chunks of material, we should see a smooth transition in the observations. We should see the swarm gradually dispersing, individual fragments spreading out along different trajectories as their slightly different velocities cause them to separate over time. We should see the structure becoming more diffuse and less defined as days pass. Instead, we see sharp changes, sudden transitions. The flip is a discontinuity, a sudden change in the visual presentation of the object that correlates with its passage through the intense gravitational field and solar heating of perihelion. It's not a gradual evolution. It's a discrete event where the configuration changed abruptly from one state to another, suggesting that something happened during or shortly after perihelion that reorganized the swarm structure. The anti-tail is currently the strongest evidence we have that 3I Atlas is not just a fluffy snowball, not a loosely consolidated rubble pile of the kind we think most comets are. It is a solid, dense object, or at least contains solid, dense components, capable of shedding large debris fields that maintain their cohesion over distances of millions of kilometers. The mere existence of this swarm, regardless of its exact composition or origin, tells us that this object has internal structure, has differentiation between components with different strengths and different volatilities. And as we approach December 19th, as the angle of observation shifts to place us in optimal viewing geometry, we're going to learn much more about the density distribution of this swarm, about whether it's a single cloud or multiple distinct concentrations, about how the brightness varies across its extent, about what spectroscopic signatures we can detect from material within it. These observations will either constrain the swarm to natural explanations, will allow us to construct models of fragmentation or ablation that reproduce what we see, or they will deepen the mystery further, will reveal additional properties that are difficult to reconcile with conventional processes. But the anomalies don't stop at the physical structure and the puzzling behaviour of this persistent swarm. If the spider jets are the visible engine driving activity, if the swarm is the massive wake left behind, then we need to examine the fuel, the energy budget, the power source driving all this activity. And that brings us into the invisible spectrum, into wavelengths our eyes can't see but our instruments can detect, revealing energy signatures that are incredibly rare for comets, that suggest processes more violent and energetic than simple sublimation of ice under solar heating. The latest observations coordinated across multiple facilities have picked up something that is virtually unprecedented for cometary objects, something that required specialized space-based instruments designed specifically to detect high-energy radiation. We are seeing X-ray emissions from 3I Atlas. As we established in our discussion of the visible morphology, the physical behavior is bizarre, jets and swarms and flips that don't match standard models, but the chemical and energetic signatures are about to throw another massive wrench in the works, are about to reveal that this object is not just unusual in how it looks, but in what it's doing at an atomic and molecular level. We are seeing high-energy interactions that simply shouldn't be happening at the intensity we're measuring. We are seeing color changes in the coma that indicate a fundamental shift in chemical composition on timescales of days. The object is changing its skin as it travels, revealing different layers or different reservoirs of material. Building on the structural and behavioral anomalies, the next piece of this, increasingly complex puzzle lies in analyzing the light spectrum, in breaking down the electromagnetic radiation into component wavelengths, and examining what elements and molecules are present and in what excitation states. The comet has turned green, but not just any generic green glow like you might see from algae or aurora borealis. This is a specific highly diagnostic signature of diatomic carbon molecules, C2, that tells us something profound about the gases being vented from the interior, about the chemistry happening in the coma as solar ultraviolet radiation breaks apart parent molecules. And when you combine that green C2 emission with the X-ray detection we mentioned, when you layer these observations together, you get a picture of an object that is interacting with the solar environment in a way that is almost aggressive, that seems to be fighting back against solar wind bombardment with massive gas production. This connects directly to the idea of the chemical engine concept. If the spider jets are the exhaust, the visible manifestation of whatever is happening inside the nucleus, then what is the reaction driving them? What chemical or physical process is generating the energy and pressure to produce those violent episodic outbursts? Why is there so much nickel in the emission spectrum? Why are we detecting X-rays at intensities that require either very dense gas or very hot plasma? These questions don't have obvious answers within conventional cometary science, and that's forcing researchers to think more creatively about what might be happening. In the next chapter, in our continued investigation of 3I Atlas, we're going to dive deep into the spectral analysis, into the wavelengths of light that reveal chemical fingerprints. We're going to examine what astronomers are calling the blood of the comet, the compositional signature that defines what this object is made of and where it might have formed. And we are going to discover that it is running hot in ways that natural processes struggle to explain, exhibiting an energy budget that seems excessive for simple solar heating, suggesting either exotic volatile compositions or perhaps something more enigmatic, generating internal heat from sources we can only speculate about until we have more definitive data from the high-resolution spectroscopy that Hubble and JWST and X-RISM are about to provide as they turn their powerful eyes toward this mysterious visitor from beyond our solar system. We have covered the spider jets erupting chaotically from the nucleus and the mysterious swarm anti-tail maintaining coherence despite forces that should disperse it. We have established that physically, structurally, morphologically, 3I Atlas is behaving like nothing we've seen before, like a rigid volatile object shedding heavy debris while simultaneously experiencing violent episodic outbursts. But to truly understand what is happening inside that nucleus, to comprehend what processes are driving the observed activity, we have to look beyond the visible structures, beyond what our eyes can see even aided by the most powerful optical telescopes. We have to examine the light itself, the electromagnetic radiation across wavelengths from X-rays through ultraviolet and visible into infrared, breaking it down into component frequencies and analysing what that spectrum tells us about chemistry and energetics and temperature. And the latest spectral data from December 14th, collected from multiple observatories coordinating their observations to build a comprehensive multi-wavelength dataset, reveals a chemical engine that is running on a very strange fuel mixture, exhibiting emissions that shouldn't be possible from simple ice sublimation, generating an energy budget that exceeds what passive solar heating can provide. Let's look at the X-ray emissions first, because this is genuinely a headline in itself, an observation so unusual that it merits careful explanation. Comets are cold objects fundamentally. They form in the frigid outer reaches of stellar systems where temperatures are measured in tens of Kelvin, barely above absolute zero. They are icy bodies composed primarily of frozen volatiles that only become active when solar heating warms them enough to drive sublimation. They do not typically emit X-rays on their own through any intrinsic process. X-ray emission requires either extremely high temperatures, millions of degrees like in stellar corona, or accretion disks around compact objects, or it requires high-energy particle collisions that can ionize atoms to high-charge states. Comets don't have these conditions naturally. They're too cold, their internal structure too simple. So when we do see X-rays from a comet, and this is rare enough that each detection is noteworthy, it is usually the result of a process called charge exchange that was only discovered and understood in the 1990s. This happens when highly charged ions in the solar wind, particles streaming outward from the sun at hundreds of kilometers per second, slam into the neutral gas atoms in the comet's coma. The solar wind contains ions that have been stripped of multiple electrons by the intense heat and radiation near the sun's surface. Ions of carbon and oxygen and nitrogen in high-charged states like C6T or O7 where most of the electrons have been removed. When these highly charged ions encounter neutral atoms in the coma, atoms that still have all their electrons, a process occurs where the ion steals captures an electron from the neutral atom. This charge exchange reaction releases energy as the captured electron drops down into a lower energy orbit around the ion, and that energy emerges as an X-ray photon. The specific wavelength of the X-ray, its energy, depends on which ion captured the electron and which orbital the electron settled into. By measuring the X-ray spectrum, by identifying which emission lines are present, you can determine what ions are in the solar wind and what neutral atoms they're colliding with. It's a beautiful diagnostic of solar wind composition and cometary coma density. The fact that we are seeing a strong X-ray signal from 3I Atlas confirms unambiguously that the gas envelope is incredibly dense and active. This isn't a wisp of gas, a tenuous, barely there atmosphere. This is a thick shield, a substantial coma containing enough neutral atoms that solar wind ions collide frequently enough to produce detectable X-ray emission. The interaction is violent in the sense that these collisions are energetic, that the relative velocities between solar wind ions and cometary gas atoms are hundreds of kilometers per second, creating conditions for efficient charge exchange. This enhances and quantitatively supports the assessment of high gas activity that we noted earlier when discussing the spider jets. But it's the intensity of this X-ray emission that is really catching attention from researchers familiar with cometary X-ray observations. The X-ray luminosity, the total power emitted in X-rays, is higher than what models predict based on the estimated size of the nucleus and typical cometary outgassing rates. It suggests a volume of gas production that rivals much larger comets, despite 3I Atlas having a relatively small nucleus, estimated at only a few kilometers diameter based on brightness and assumed albedo. This implies either that the outgassing rate per unit surface area is extraordinarily high, much higher than typical comets achieve, or that our size estimate is wrong and the nucleus is actually larger than we think. Both possibilities raise questions. If the outgassing rate is extreme, what drives it? What composition or structure allows such prolific gas production? If the nucleus is larger than estimated, why does it appear so compact in images? Why don't we see more diffuse emission from a larger surface area? But the visible spectrum is where the story becomes even more interesting and colourful, literally, where we see signatures that tell us about composition and chemistry in ways that X-rays alone cannot. New images processed from observations over the last few days show a distinct greenish tint to the coma, a colour that's immediately recognisable to comet observers as the signature of C2 molecules, diatomic carbon. Two carbon atoms bound together, vibrating and rotating, absorbing solar ultraviolet radiation and re-emitting it in the green part of the visible spectrum around 510 to 520 nanometers. Now, green comets are not unheard of. We've seen them before. Some of the brightest comets in history have shown this green coloration. Comet Lovejoy in 2015, Comet Lulin in 2009, several others. The green comes from C2, which forms when larger carbon-bearing molecules in the coma get broken down by solar UV radiation, photodissociation producing C2 fragments that then fluoresce. But it's the timing of this green emission and the shift in colour that matter enormously here. that tell us something profound about what's happening to the nuclear surface. Before perihelion, back in July and August when 3I Atlas was first discovered and characterized, the object had a distinct reddish hue in color images. Red coloration in solar system objects usually indicates the presence of tholins, complex organic compounds that have been irradiated by cosmic rays and solar UV over billions of years. These tholins are created when simpler organics, molecules like methane and ethane and propane, get bombarded with high-energy radiation that breaks bonds and allows atoms to recombine in larger, more complex structures. The resulting compounds absorb blue light preferentially and reflect red, giving objects a characteristic reddish-brown color that we see on many outer solar system bodies like Pluto's surface or Titan's atmosphere. Red is the color of age, the color of material that has been exposed to the space environment for eons, the color of the outer solar system, where organic chemistry proceeds slowly under low temperatures and weak sunlight. So the fact that 3I Atlas was red when first discovered made sense. It looked like an ancient object, something that had been wandering through interstellar space for millions or billions of years, accumulating cosmic ray damage and building up surface tholins. So what does this color shift from red to green actually mean? What does it tell us about the evolution of this object as it passed through perihelion? It means fundamentally that the comet has shed its old skin, that outer layer of aged irradiated material. The intense heat of the sun during perihelion passage has vaporized that ancient red crust, sublimating away the surface material that contained the tholins, and now we are seeing deeper layers, fresh volatile rich material from the interior that hasn't been exposed to radiation for billions of years. The shift from red to green is a sign of unmasking, a revelation of the comet's heart, its primordial composition preserved in the deep interior and only now being exposed to solar heating for the first time since the object formed. And this green glow, this C2 emission, is intensifying specifically in the anti-tail region, which is absolutely fascinating and adds another layer to our understanding of what that swarm actually is. Usually cometary tails are coloured by different processes than the coma. Dust tails appear yellowish-white because they're just reflecting sunlight off dust particles. Ion tails appear bluish because they contain ionized carbon monoxide, CO+, which has strong emission bands in the blue part of the spectrum. To see the C2 signature, the green emission, intensifying in the antitail region suggests something profound and unexpected. It suggests that the swarm we discussed in the previous section is not just dry rock, not just inert fragments of solid material tumbling through space on ballistic trajectories. It is outgassing. The chunks of material in the antitail swarm are themselves actively releasing gas, producing C2 emission as their surfaces warm and volatiles sublimate. This completely contradicts what we previously thought about the antitail being purely heavy debris. If it is glowing green, if it is showing C2 emission, that means the debris contains volatile material, ices or organics that are still sublimating even after being ejected from the main nucleus. This implies that the fragments are either freshly broken, exposing interior material that still retains volatiles, or that they're heated internally somehow, maintaining temperatures high enough to drive sublimation even at large distances from the sun. Both possibilities are intriguing and both raise questions about the ejection mechanism and the nature of the nuclear structure. And then there is the detailed composition revealed by spectroscopy, by spreading the light into its component wavelengths and identifying which atoms and molecules are present based on their characteristic emission or absorption lines. The spectral analysis from multiple teams is picking up signatures that are raising eyebrows among researchers who know what typical cometary spectra look like. We are seeing strong indications of methanol, CH3OH, a simple organic molecule that's common in comets. We're seeing hydrogen cyanide, HCN, another typical cometary volatile that's detected in most active comets, and serves as a tracer for more complex organic chemistry. We're seeing carbon dioxide, CO2, one of the major volatile species along with water ice that comprises cometary nuclei. These detections are expected, consistent with normal cometary composition. But there are oddities, deviations from typical abundances, ratios between species that don't match what we see in solar system comets. And most puzzling of all, most difficult to explain through standard formation models, we're seeing elevated nickel in the emission spectrum from metallic atoms in the coma. We mentioned the nickel earlier when discussing the spider jets, but let's really drill down into why this is so chemically odd. why it's generating intense discussion among cosmochemists trying to understand where this object formed and what processes created its current composition. In our solar system, in the material that condensed from the solar nebula to form the Sun and planets and asteroids and comets 4.6 billion years ago, iron and nickel usually come together. They are the heavy metal brothers chemically, both side-ruffle elements that preferentially bond with metallic phases rather than silicates or volatiles. In meteorites, in differentiated planetary cores, in iron-nickel asteroids, these elements are always associated with characteristic ratios. The cosmic abundance ratio is roughly 17 parts, iron to 1 part nickel by number of atoms, though this can vary somewhat in different meteorite classes depending on formation, conditions and differentiation history. To see a high nickel to iron ratio, where nickel is overabundant relative to iron compared to solar system norms, is chemically odd and demanding explanation. It implies a formation history that is different from the standard accretion disk model of our solar system. It suggests that 3I Atlas was born in a place where the chemical cookbook was different, where the relative abundances of elements deviated from what we consider normal based on our local sample of one stellar system. Maybe this indicates formation in a region rich in what cosmochemists call chalcophile elements, elements that preferentially form sulfides and metals under certain temperature and pressure conditions. Maybe it reflects a stellar system where the initial metallicity, the abundance of elements heavier than hydrogen and helium, was different from our Sun. Stars that formed from gas clouds with different enrichment histories, different contributions from previous generations of supernovae, can have significantly different elemental ratios. Or maybe it suggests differentiation processes that separated iron from nickel in ways we don't typically see in our solar system, perhaps due to different planetary formation dynamics or different timing of giant impacts. The presence of methanol and HCN is also scientifically significant, beyond just confirming that 3I Atlas is outgassing organics. These are prebiotic molecules, chemical building blocks that are considered essential precursors to the origin of life. Methanol can participate in reactions that build more complex organics. HCN is a key intermediate in amino acid synthesis through what's called the Strecker synthesis. Finding these molecules in interstellar objects tells us about the organic inventory of other stellar systems, about whether the chemistry that led to life on Earth is common throughout the galaxy. But in the specific context of understanding 3I Atlas's chemical engine, methanol and HCN represent volatiles that sublimate at different temperatures than water ice. This is crucial. Water ice, H2O frozen solid, requires temperatures above about 180 Kelvin to sublimate at the low pressures of space. That's minus 93 Celsius, cold by Earth standards but warm compared to interstellar space. Methanol ice can sublimate at lower temperatures around 100 Kelvin. HCN is even more volatile. CO2 sublimates readily at 150 Kelvin. The fact that we are seeing all of these species simultaneously, that we're detecting emissions from molecules with very different volatility, mixed together with high temperature emissions from metals like nickel that require vaporization temperatures above 1000 Kelvin, this suggests a chaotic internal structure. The nucleus is not a neat stratified layer cake of ices where the most volatile species are on the outside sublimating first, then progressively less volatile species as you go deeper. Instead, it's a marble cake, a jumbled, heterogeneous mix where deep freeze volatiles like HCN are trapped, adjacent to refractory metals, where pockets of different compositions exist side by side without the smooth gradients you'd expect from thermal equilibration. This unusual heterogeneous composition might explain the spider jets in a natural way that doesn't require invoking anything exotic. If you have pockets of highly volatile material like HCN or CO, trapped inside a matrix of less volatile water ice mixed with rock and metal, when solar heat penetrates to those volatile pockets, they don't just gently melt or sublimate, they explode. The rapid phase transition from solid to gas, the large volume expansion as molecules break free from the ice lattice, this creates enormous pressure if the gas can't escape immediately. It's like having sealed bubbles of compressed gas inside a solid structure. When the seal breaks, when fractures reach those pockets, the pressure is released explosively, violently ejecting material at high velocity. These are the pressure bombs we hypothesized earlier, and the heterogeneous composition provides a natural mechanism for creating them. The chemical engine is unstable, prone to these violent episodic eruptions because the fuel is mixed poorly, because the nucleus structure doesn't allow smooth thermal equilibration and controlled sublimation. Building on this understanding of compositional heterogeneity and chaotic structure, the asymmetry we observed in the coma, those cyclone-like swirling motions, makes perfect sense. If one hemisphere of the nucleus is rich in CO2 ice, and the other hemisphere is dominated by methanol or water ice, they will sublimate at different rates when exposed to the same solar heating. CO2 begins outgassing at larger solar distances when temperatures are still relatively low. Water ice doesn't become active until the comet gets much closer to the Sun where heating is intense. This creates uneven thrust across the nucleus surface. One side is producing copious gas and experiencing strong reaction force pushing the nucleus in the opposite direction, while the other side is relatively inactive. The nucleus isn't just melting passively, it is being pushed around by its own exhaust, experiencing asymmetric forces that create torques and accelerations beyond what gravity alone produces. This is the rocket effect, non-gravitational acceleration, produced by asymmetric outgassing, and we'll examine this in quantitative detail when we discuss orbital dynamics. This connects directly to the next major anomaly that's becoming increasingly difficult to ignore as more precise astrometric measurements accumulate. The movement, the trajectory, the actual path this object is following through space. We have a chemically complex object firing jets randomly in multiple directions, shedding a swarm of active debris that's glowing green from C2 emission, producing X-rays from violent solar wind interactions. All of these processes, all of these activities, the jets, the outgassing, the solar wind bombardment, they impart forces to the nucleus. They push it. They change its momentum. They modify the trajectory in ways that gravity alone cannot. And this brings us to what astronomers call asymmetric drive, to the measurements showing that the orbital parameters are shifting in ways that purely gravitational models cannot predict. The math isn't lining up when you calculate where the comet should be based solely on the gravitational attractions of the Sun and planets. When you integrate Newton's laws or Einstein's general relativity equations forward in time, using the precisely measured positions from weeks ago as initial conditions, you get predictions for where the comet should be today. And then you observe where it actually is, and there's a discrepancy. The comet is deciding in effect to be somewhere slightly different than pure gravity says it should be. These discrepancies are called non-gravitational accelerations, and for 3I Atlas they are not just present but remarkably large, significantly exceeding what typical comets show. In the next chapter, in our continued deep dive into this mystery, we are going to look at the detailed physics of this motion. We are going to talk about the parameters that astronomers use to quantify non-gravitational forces, the technical terms A1 and A2 and A3 that describe accelerations in radial, transverse and normal directions. We are going to examine how these parameters are measured and what values 3I Atlas is showing. And we are going to find that the chemical engine we've described, this chaotic, heterogeneous mix of volatile ices and refractory materials producing violent episodic outbursts, is driving the comet along a path that looks suspiciously like organized asymmetry rather than random perturbations. The jets aren't firing randomly. They're producing a net thrust vector that has specific directionality. The result is motion that appears almost navigated, though we must be very careful not to jump to conclusions about what that might mean. We have analysed the spider jets as the visible engine, the swarm anti-tail as the massive wake left behind, and now the chemical composition as the exotic fuel mixture driving this activity. The picture that emerges is of an object that is profoundly unusual across every measurement we can make, every observable we can quantify, but observations without dynamics are incomplete. We need to understand how this object moves, how the forces we've documented translate into trajectory changes, how the asymmetric outgassing creates momentum transfer that modifies the orbital path. The movement of 3I Atlas, the deviations from purely gravitational motion, these are perhaps the most compelling evidence that something extraordinary is happening, that this is not business as usual for comets. Because while you can construct elaborate explanations for individual anomalies, while you can propose special circumstances and unusual but natural compositions that might explain the jets or the swarm or the X-rays individually, when you look at the motion, when you see trajectory modifications that correlate with activity in ways that seem too precise to be accidental, the cumulative case for something genuinely anomalous becomes overwhelming. Part 4 awaits, our final chapter in this emergency analysis of December 14th developments, where we will examine the asymmetric drive in detail, where we will quantify the non-gravitational forces and show just how unusual the motion pattern is, where we will discuss the rotation state and why the brightness variations don't match expectations for natural tumbling, where we will look at what Hubble and Gersum observations scheduled for the coming days might reveal, and where we will finally confront the question that has been hovering over this entire discussion. Given everything we've documented, given the spider jets and swarm anti-tail and exotic chemistry and anomalous motion, given that every single measurement reveals something unexpected, what is the most parsimonious explanation? Is this just a very unusual but ultimately natural comet, a statistical outlier that exhibits multiple rare properties simultaneously? Or have we crossed the threshold where natural explanations require so many coincidences, so many special circumstances, that alternative frameworks must be seriously considered? The data is what it is. The observations are real. The measurements are reproducible. What remains is interpretation, and that's where the scientific debate is now focused, where researchers are grappling with how to make sense of an object that doesn't fit cleanly into any category we've established, that challenges assumptions we didn't know we were making about how interstellar visitors should behave. That reminds us that the universe is under no obligation to present us with phenomena that match our expectations, but instead confronts us with reality in all its strange and wonderful complexity, demanding that we expand our frameworks or build new ones adequate to encompass observations that refuse to be explained away through conventional thinking and comfortable assumptions. We have arrived at the final chapter of our investigation into the December 14th developments surrounding 3I Atlas. We have dissected the anatomy of this object from its spider jets and swarm anti-tail to its exotic chemical engine, showing elevated nickel and X-ray emissions. The data is undeniable, the observations reproduced by multiple independent teams, using different instruments at different locations. This object is an anomaly among anomalies, exhibiting behaviours across every measurable parameter that deviate from what we expect based on decades of cometary science. But data without interpretation, observations without context, measurements without physical understanding, these leave us with a catalogue of strangeness but not comprehension. Now we must synthesize these findings into a coherent framework. We must examine the one aspect we've only touched on briefly, but which may be the most telling signature of all: the movement, the trajectory, the path this object is carving through space under forces that are not purely gravitational. And we must face the question that is dividing the scientific community, generating heated debates in conference halls and academic departments, sparking passionate arguments between researchers who have dedicated their careers to understanding comets. What are we actually looking at? Let's start with the movement, because this is where mathematics becomes unavoidable, where we transition from qualitative descriptions of unusual behaviour to quantitative measurements of forces and accelerations that can be compared against models and tested against predictions. If 3I Atlas were following a purely gravitational trajectory, if the only forces acting on it were the gravitational attractions of the Sun and planets, then its path through space would be completely deterministic, perfectly predictable given sufficient initial measurements. Astronomers parameterize non-gravitational forces using the Marsden-Sekanina formalism, expressing acceleration as a vector sum of components in three directions relative to the Sun. A1 represents the radial component, acceleration directly away from or toward the Sun. A2 represents the transverse component, acceleration along the direction of orbital motion. A3 represents the normal component, acceleration perpendicular to the orbital plane. For typical comets, A1 dominates, often 10 to 100 times bigger than A2, while A3 is negligible. Now here is where 3I Atlas becomes extraordinary. The updates as of December 14th show anomalous values across the board, not just A1 being large, but A2 and A3 being unusually strong, sometimes comparable to A1 in magnitude. This contradicts expectations. If outgassing was simply responding to solar heating, the time-averaged effect should be dominated by the radial component. But for 3I Atlas, the transverse and normal components persist, implying stable preferred directions maintained over long timescales. And here is the critical mystery. The nucleus rotation does not cause the expected blurring that strong off-axis forces should produce. The spider jets remain distinct. The swarm anti-tail remains coherent. We see organized structure where we should see chaotic smearing. Something doesn't add up. Fresh data reveals an asymmetrical coma, where the luminous nucleus is compressed and offset from the center of the gas envelope. The envelope is shifted, displaced, with the nucleus at an eccentric position. This confirms the outgassing is highly localized, concentrated in specific regions, perhaps even discrete vents firing from fixed locations not aligned with solar heating patterns. The brightness changes are pulses of thrust. Every spike means fresh ejection carrying momentum away. The comet is a natural rocket with stuck throttle and wobbling nozzles. These accelerations accumulate, building velocity changes that compound daily. The comet is no longer following pure gravity. It's being nudged, pushed, steered by its own activity in directions we measure but struggle to predict. Avi Loeb has emphasized that combining all evidence, trajectory precision toward Jupiter's hill radius, anti-tail flip, jet directionality including sunward pointing, high A2-A3 parameters, produces a motion vector that is complex, structured, organized rather than random. Not maneuvering in the sense of intelligent control necessarily, but maneuvering as complex interaction producing motion that looks organized rather than chaotic. The organized asymmetry is key. Random noise looks like static. This looks like structure. Jets diverge at large angles from solar direction, implying internal heat distribution profoundly different from surface illumination, or geologically constrained vents opening along fracture planes regardless of where the sun is. The rotation paradox deepens. High thrust should mean high torque, spinning the nucleus faster until centrifugal forces cause breakup. Yet brightness variations suggest 8 to 12-hour periods, relatively sedate despite forces that should accelerate spin. How is this possible? High moment of inertia, cancelling torques, or controlled damping through internal structure converting rotational energy to heat? This resilience matters. The object hasn't fragmented despite violent outgassing, hasn't spun up to break up despite strong torques, maintains structural integrity and organized behavior under conditions that should produce chaos. So let's address the elephant in the room. We have comprehensive anomalies, spider jets, swarm anti-tail, X-rays, green C2 from ejected fragments, elevated nickel, heterogeneous composition, offset nucleus, non-gravitational accelerations, organized structure, stable rotation, structural integrity. Is this just a weird comet, a statistical outlier, or something else? The line between natural anomaly and artificial signature is defined by Occam's razor. For any individual anomaly, the simplest explanation is natural. But at what point do accumulated coincidences become more improbable than considering alternatives? The mainstream consensus, 3i Atlas, is natural. A new type of comet, exotic composition, but fundamentally a product of natural cosmic evolution. This position grounds itself in requiring extraordinary evidence for extraordinary claims. Claiming artificial origin implies technological civilizations, interstellar capabilities, their hardware in our solar system. Such claims demand evidence definitively ruling out all natural explanations. The natural interpretation, extreme physics produces extreme outcomes. Spider jets are irregular erosion. Swarm is disruption from thermal stress. X-rays, from dense coma charge exchange. Nickel reflects different stellar metallicity. Every anomaly has or will have natural explanation. The mystery is a puzzle for better modelling, not indication of artificiality. On the other side, Loeb and growing numbers argue we're engaged in confirmation bias, forcing square pegs into round holes, dismissing anomalies as weird natural, without proving natural mechanisms can actually produce observations. He emphasizes trajectory precision. How can random interstellar trajectory aim at specific dynamically significant location with beyond coincidental accuracy? Why does anti-tail look like discrete object swarm? Why organize thrust rather than random outgassing? His position isn't that it's definitely artificial, but that the possibility deserves serious consideration as working hypothesis tested against data rather than dismissed a priori. Why assume interstellar probes are vanishingly rare when we have no data on civilization frequency or exploration strategies? As anomalies accumulate, researchers reach for exotic natural explanations. Dark comets, nitrogen ice, metallic hydrogen, even dark matter interactions or sterile neutrinos. When you invoke unconfirmed physics to explain a comet, when unusual natural requiring new physics becomes your explanation, at what point is that more extraordinary than manufactured object from another civilization? This is the intellectual crisis 3i Atlas creates, forcing examination of assumptions about plausibility, probability, possibility. What does this mean for us? We're in fundamental uncertainty with multiple futures depending on coming observations. We await the cosmic verdict from premier instruments. Hubble Space Telescope has scheduled time, will provide resolutions ground-based cannot match, resolving coma structures down to hundreds of kilometers, imaging individual swarm components if they exist as discrete bodies. If spider jets are discrete directional features, Hubble will show them. If swarm is large fragments, Hubble will detect them individually. X-RISM will analyze X-ray spectrum with unprecedented resolution, identifying exactly which elements are ionized, measuring charge states precisely, determining if emission is purely charge exchange or includes thermal or other contributions. If there are internal heat source signatures, X-RISM will find them. If Hubble shows metallic debris, the artificial debate explodes. Metal doesn't belong in comets. If X-RISM shows thermal X-rays indicating millions degree temperatures, that implies energy beyond solar heating or charge exchange. If spectroscopy detects unnatural molecules or two uniform isotope ratios, burden of proof shifts dramatically. Conversely, if Hubble shows crumbling ice, if X-RISM confirms pure charge exchange, if spectroscopy matches interstellar chemistry perfectly, natural explanations validate. Until data arrives, we're in twilight zone. My assessment, 3i Atlas is a messenger regardless of origin. It tells us interstellar medium is full of surprises, that passing objects exhibit diversity we haven't appreciated, that our understanding of possible nature or technology is incomplete. Comet feels inadequate for this complexity. We need richer taxonomies handling edge cases and hybrid objects challenging binary categories. The universe is messy, producing things that challenge frameworks. Our job is following evidence honestly, updating beliefs when data demands, acknowledging uncertainty while reducing it through observation. December 19th brings optimal geometry, Hubble and X-RISM data arriving in days, weeks. Analysis takes time, but preliminary results will leak. We'll know more soon about whether swarm is debris or something else, whether X-rays hide secrets, whether chemistry requires exotic explanations. If you found value in this analysis, engage with this content. Like, share, comment with your interpretations. This is investigation happening in real time where public attention matters, where demanding transparency and honest anomaly engagement serves everyone. Keep watching the skies. They're speaking, presenting phenomena, testing understanding, challenging assumptions, reminding us the universe is stranger than theories accommodate. Check description for raw data links, papers, astronomical telegrams reporting observations as they happen. The next weeks will be historic regardless. Either confirming nature produces stranger phenomena than imagined, or confronting evidence forcing us to consider we're not alone, that intelligence exists beyond Earth, that technology from other civilizations occasionally passes through leaving detectable signatures. Both possibilities are profound. Both deserve careful attention. Both remind us why astronomy matters, why we scan skies, why understanding cosmic context is among humanity's most fundamental questions. Thank you for following this journey through spider jets, swarm anti-tail, chemical engine, asymmetric drive. Thank you for engaging with complexity rather than demanding premature certainty. Thank you for being part of this moment when data forces questioning whether our categories adequately describe what's actually out there. The universe continues regardless of whether we understand correctly. Our best hope is maintaining intellectual humility, following evidence honestly, never assuming we've seen everything nature or anyone else can produce. The moment we stop being surprised is the moment we stop learning, stop discovering, stop expanding human knowledge into territories we can't anticipate, but can explore if we maintain curiosity and courage and commitment to truth, regardless of where it leads or what comfortable assumptions it forces us to abandon in service of aligning belief with reality as it actually is, rather than as we wish or expect it to be.